Hello everybody, welcome to the lecture series Foundation for VLSI Design. This is the fifth lecture, and in this lecture we'll be continuing with the digital systems. Specifically in this lecture we'll be looking into finite state machines or FSMs. So first we'll be looking into the definition of FSM, then its representation, then we'll look into a few examples of FSM, and then finally we'll also look at an implementation of FSM. Now first let us look into the definition of an FSM. So what is an FSM? So FSM is an abstract mathematical model to represent wide variety of sequential circuits and systems. So you should note that FSM is widely used in engineering, right? Not only to represent sequential circuits and systems, but also it is used at various places in computer science, electronics, to describe biological processes, and also it is used in linguistics, right? So FSM is a very powerful mathematical tool to analyze various kinds of systems, and sequential systems or application of FSM in sequential systems circuits is one of the examples, right? Now what does an FSM consist of? Let us look into it. So an FSM consists of finite non-empty sets of inputs, outputs, and the states. And how do we model the states in a sequential circuit? So we model it and using flip-flops, right? So in earlier lectures we had seen that the combination of values at the q pins of the flip-flops in a sequential circuit, that is considered as the state. So states are in a sequential circuit is typically modeled using the values at the q pins of the flip-flops in the circuit that represents an FSM, right? Then for an FSM, out of all the states given, an initial state is given, right? So given there can be say 100 states in an FSM. Out of it, one of the state will be considered as the initial state, and that is defined for an FSM. In addition to input, output, and the states, there is one more component, and that is very important, and that is what is known as state transition function, or represented as delta. So what is state transition function? So a state transition function basically describes how an FSM transitions from one state to another, right? So you should note that given a state and an input, the FSM will transition to some state. Like now, which of the, say there are 100 states in an FSM. Now from a given state and a given input, where to which state it will transition to, that is represented by the state transition function, right? So it is this function is a function of current state and the current input, right? So this is a mapping between the current state and the current input to the next state, right? So this is what the state transition function is. A state transition function maps current state and the input to the next state. And this state transition model is state transition function is modeled using combinational circuit. So we saw that how do we model the states? We model the states using flip-flops. And how do we model the state transition function? We model using combinational circuits, right? So when we design an FSM, this is the major part of effort goes into, right? So the designer's major effort, or the tool which is making a circuit for a given FSM, the major effort goes into deciding that what should be the characteristics of this combinational circuit that will actually model the state transition function. Now an FSM also consists of an output function. So what is an output function? Output function can be modeled in two ways, right? There are two ways to model the output function. What are the two ways? The first one is that output is the function of the current state only, right? So given a state, there is an output associated with, right? For example, there is a state, say there are 100 states in an FSM. out of it, say the state is S9, right? Just I took any name, arbitrary name. S9 is there. Now at S9, what the FSM should output should be? It can be a binary number or it can be something else, right? So an output is a function of the current state only in this case, and when that is the situation, then we call the FSM as the Moore machine, right? And there is another way to model the output function, and in the other way is that it is a mapping between the current state and the current input, right? So it is the output is a function of the current state and the current input. So the output function will be modeled as, say, this is the current state and this input comes, then it will produce this particular output. When that is the case, then it is this FSM is known as the milli machine, right? So now let us look into that. Now we have seen that what is the definition of an FSM. Now let us look into that how can we represent an FSM in a better way so that it is easy to understand. So we can represent an FSM pictorially using a directed graph, and this directed graph is known as state diagram. So we'll see an example of state diagram, then it will become much easy to understand. So what is a state diagram? So state diagram is a directed graph, and a graph consists of vertices and edges, right? So we'll be looking into some more detail of graph later in this lecture series, but for now just think that a graph consists of vertices and edges shows the connections between vertices, and vertices are some entities which are no which exist in a graph, right? So when we want to model an FSM using state diagram, then the states correspond to the vertices in the graph, right? And then the transition from one state to another is represented by the edge in the graph. So the edge starts from the current state and ends in the next state, and the input is marked on the edge, right? So what we want to say is that suppose we want to our FSM consists of only two states, right? So one state is this, we call it as state 1, and another state is state 2, right? So if we in this state in FSM there is a transition from state 1 to state 2, when an input 1 comes, then we represent it using, say, these two circles. These are vertices, those represent the states, right? And this edge, that is the arrow goes from one vertex to the other, this is the edge, and this edge represents the transition from the state 1 to the state 2. And when does this transition come, or when does this transition occur? This transition occur when an input 1 comes and the current state is state 1, right? So the arrow is from the state 1 to state 2. It means that the transition is from state 1 to state 2, right? And we saw that the output is modeled in two different ways. Now if the machine is a Moore machine, so remember that we discussed that in a Moore machine the output is function of only the states, right? So if that is the case, then the output value is simply marked inside the state for a Moore machine, right? So in this case the output will be marked that output 1 when the state is state 1, when the state is state 2, then it is producing another output 2, right? So this is for the Moore machine. Now how will the state diagram look for or appear for a milli machine? So we discussed that in a milli machine the output is a function of the current state as well as the input, right? So in that case the output is not mentioned in the vertices or the states, but it is mentioned at the edges or in the transition where input also appears, right? So for a milli machine the state diagram will look like something like this. The state will be there, right? Then the transition will be there, that from state 1 to state 2 the transition happens when the input is 1, right? Now the output here is mentioned on the edge, right? So what does this mean? It means that whenever there is a state 1, the current state is state 1 and the input 1 appears, then the output produced will be output 1, and the state will now go to state 2, right? This is the meaning of this representation of the state diagram, representation using state diagram for a milli machine, right? So the difference in the representation for Moore and milli machine is only for the output. In the Moore machine, the output is mentioned in with the states, and in the milli machine, the output is mentioned at the edges. Now let us look into an example of an FSM, right? To give an example, I consider a simple fan regulator. So note that it is a very simplistic model, right? So a fan regulator can be described as an FSM. So the fan regulator that we usually have at our home, and in which the control is discrete. In that case, we can model the fan regulator using FSM. So suppose that in the fan regulator there were 4 settings, right? So those settings, 4 settings, can be represented as 4 states, right? For example, S0, S1, S2, and S3. These are 4 states, right? So, and we can say that, say, S0 is the initial state. This is an arbitrary in this case. So we say that S0 is the initial state, and S0, S1, S2, S3 are the 4 states in which the regulator can be there, right? Now, when we want to change the settings, right, we either rotate it clockwise or we rotate it anti-clockwise. So this is an example of a fan regulator in which the control is discrete, and when we rotate it clockwise, then it goes to from one state to the other, right? So input to the regulator is it can be either rotate clockwise or rotate anti-clockwise in a circular manner, right? uh, so the inputs to the FSM are, say, we represent the clockwise movement as C and A as the anti-clockwise. So we represent the inputs as C and A. Right now, 4 different speeds at 4 settings are the outputs of the FSM. Now let us assume that in this FSM there are 4. This FSM is producing 4 different speeds. So at S0 the speed is speed 0, at S1 speed is speed 1, S2 the speed is speed 2, and S3 is speed 3. Right. So these are speed 0, speed 1, speed 2, speed 3 are 4 different outputs that are produced by these 4 different states, S0, S1, S2, S3. Right. Now, how will the state transition diagram look like for in this case? So so in this state transition diagram will do something like, say, if there is a state S0, right, and if we rotate, say, clockwise, then it goes to, say, S1, then again clockwise it goes to S2, and again clockwise to S3, and again clockwise, then in circular manner it goes to S0, and so on. And similarly, it can be rotate anti-clockwise successively. From S0 it goes to S3, then again to S2, and then S1, and then finally again to S0. So these are the states, transitions, right? Now first let us understand that how we can represent this FSM, which this description is a mathematical model of an FSM. Now let us draw the state diagram for this, right? So let us draw the state diagram for this. So we can, so in this figure we are showing the state diagram for the FSM, for which the mathematical model was shown earlier, right? So we have 4 states, so we have 4 vertices in this state diagram: S0, S1, S2, S3, right? And then we have the transitions, that S0 clockwise movement it goes to S1, S1 clockwise movement it goes to S2, S2 clockwise movement it goes to S3, and clockwise again to S0. So it is a circular movement, right? Similarly, anti-clockwise from S0, anti-clockwise go to S3, S3 to S2, S2 to S1, and S1 to S0, right? So this is how the transition happens in both the directions, right? Now in this case we said that for the state S0 the speed is speed 0, S1 is speed 1, and S3 is S2 is speed 2, and S3 is producing speed 3, right? So we can mark these all three speeds at the states, right? So since this speeds are associated with the states, we can mark it on the vertices, right? Now which kind of this machine is this FSM? Is it a Moore machine, or is it a milli machine, right? So we have discussed that since the output depend only on the current state, this is an example of a Moore machine, right? Now let us look into an example of a milli machine. So let us consider an input alphabet detector, meaning input repeat detector, right? So suppose there are only two alphabets possible, A and B, right? And the task of the FSM is to produce an output 1 if the input is repeated, else it is 0, right? For example, if A was the current input and A comes, right, then it is repeated, and in this case the output should be 1, right? And suppose A was the first alphabet, and then if the input comes as B, then it produces an output as 0, right? So output is 1 if the input is repeated, else 0, right? So now let us understand that what will be the transition, how will the state transition occur, and how will this FSM look like if we draw the state diagram, right? So we construct an FSM model as follows. So first we construct the mathematical model from the description that was given above. So the inputs are A and B. These are the possible inputs to the FSM. The outputs are 0 and 1, right? These only values are possible. And what are the states? We can consider that there are two states, SA and SB, and the states in this case denote what was the last input, right? For example, the current input was A, then the state will be A. SA, right? There we are saying that there are two states we are naming as SA and SP, and the FSM will be in the state SA if the last input was A. If the last input was B, then it should be in state SP, right? And how will the transition, how can we describe the state transition? So if the input is repeated, then it remains in the same state, right? It will remain in the same state but produce an output as 1 because the input is repeat, right? That is what this definition means, right? The definition or the description of this input repeat detector was that the output should be 1 if the input is alphabet is repeated, right? So if the input is repeated, then the state will be the same. Why? Because the last state was whatever and the current input is the same, so the state should be the same, but the output should be 1. Now if input is different, right, so if the input is different, then it moves to the other state, right, because the last input changes and therefore it should go in the next another state, and at the same time it should produce an output as 0, right? So this is the mathematical description of the input repeat detector. Now let us draw the state diagram for this. So this is the state diagram, how it will look like, right? So we have two states, SA and SP. Now if it is in state A and A comes, it means that it is repeating, so it remains in SA and the output is 1. Now if it was in state SA and B was the current input, right, so it means that it has not repeated and it should go to SP, right, because the last input was B and the output produced would be 0, right? Similarly, if it was in state SP, right, and B came as input, then the output should be 1 and the state should remain the same. If it was a state SP and the input A came, it means that it should go to the next state. Next state is SA and the output produced should be 0, right? So this is how the state diagram will look like for this example. Now let us understand that how can we implement it in as a circuit, right? So if we want to implement this FSM as a circuit, how it will look like. So there are a few steps that needs to be carried out while implementing an FSM. The first thing is that we assign binary values to states. So this is known as state encoding. So there are two states in this case, SA and SB. So we can simply assign 0 to 1, 1 to the other, right? So we are using only the binary numbers, right? Zeros in binary, remember that binary numbers contain only zeros and ones, right? So we assign here SA as 0 and SB as 1, and also inputs and outputs are also encoded in binary, right? So the output was already binary, 1 and 0, right? But the input was input alphabet A and input alphabet B. So we can encode A as 0 and B as 1, right? So we can use this encoding SA as 0 and SB as 1, and we can also encode the inputs as input alphabet A as 0 and input alphabet B as 1, right? And the output is already encoded in binary, right? So the first task is to encode the states, inputs and outputs in binary number form, right? Then obtain binary coded state transition table, right? So state transition table, what is state transition table? It maps the current state and the input to the next state and the output, right? So let's draw the state transition table first, right? So in this, suppose, so we have to represent all these arrows, all these arrows in this in this state diagram represents a transition. So for each transition in the FSM we must have an entry, right? So let's take the first transition. Let's take the first transition, that the current state is, in the first transition the current state is SA, right? And the input is A, right? Current state is SA, that is 0, and the current input is 0, right? So what is the next state in this case? The next state is the same, SA. So the next state is 0. And what is the output? The output is 1, right? Now let's take the other arrow from state SA, this arrow, right? Now for this arrow, we have SA is the current state, that is 0. What is the current input? Is B, right? So B is encoded as 1. So we write here as 1 is the input, X is 1. And then what is the next state? The next state is SB, which is 1, right? And what is the output? Output in this case is 0. So here we have 0. Similarly, when we are in state SB, that is 1, input is 0, right? So we are talking about this transition. So it should go to state 0, that is 0, right? So it goes to state SA, which is represented as 0. And then what is the output? Output is 0. Similarly, we consider the last transition when the state is 1 and the input is B, that is 1, and then the next state is the same, the SB or 1, and the output produced is 1, right? So we are talking about this transition, right? So the last row represent that transition, right? So now we have got the state transition table, right? Now what is the next thing? The next thing is to derive a minimize next state and output function, right? So what is the next state? So now we have to derive two functions. What are two functions? One is the next state function, right? So next state function represents the function which is a mapping between the current state and the input, right? So we have to represent the next state function and or minimize next state function, because typically we want to have a logic which is minimized in terms of area or some other measure, right? So we want to have as small number of gates in our design. So that's why we need to have a minimization, right? And then we also need to represent the output function. So first let us look into the next state function. So this is the next state function, right? And this next state function q next must be represented as a function of current state q and the input x, right? So that is what the problem is. The problem is to represent the next state as a function of the current state and the input, right? Now if we look into this the combinations here, right, if we look into the zeros and ones in next state, right, so we see that whatever is the input, same is the next state, right? So if that is the case, then we can simply write q next is nothing but x in the minimized form, right? So in this case, we find that it doesn't depend on the current state, but that is not a typical situation. Typically, q next will depend on both the current state and the input. In this case, the encoding was very simple and only two states were there, right? So we ended up in a function which is very simple, that is q next is equal to x. Now let us look into the next function, that is output z. Now how can we represent z, output z, as a function of present state and the input, right? So we have to see that here we have 1, so here both are 0. Here we have 1, we have both have 0, right? And when both are 0, we have here as 0 1 and 1 0, right? So if we write it in terms of min terms, right? So min terms for this, min term for z will be q bar x bar, representing this min term, right? And for this min term, we'll have q into q and x, right? So this is the, right? And if you remember the truth table of XOR and XNOR gate, right, that we discussed earlier, so this is nothing but, this z is nothing but an XNOR of z, sorry, this should be q, not z. So q and x, right? So this is q XNOR x, right? Q XNOR x, that is what the z is. Now once we have derived the next state function and the output function, then what will be the finally we need to do? Finally we can draw the circuit diagram, right? So how will the circuit diagram look like? In this case it is very easy, right? So here we are saying that this is x is the input, right? There is only one input, so x is the input and z is the output, and this represents the state of the circuit, right? So now what is z? Z is an XOR of, z is an XOR of sorry, XNOR of this should be q, the current state, and x, right? So that is what is represented by this XNOR gate, right? And so this is how we can represent the output function. And what is the next state function, and how will we represent it in the circuit diagram? So next state is nothing but x, right? So next state is represented by what is coming at the input d, right? Why it is representing the next state? Because whenever the clock will come, whatever was the input that will come, that what was at the d pin, that will become the next state, right? In the whenever the clock will come, right? So x is directly connected to the d pin, so that whenever the clock arrives, d will propagate to q, right? And the next state will be achieved, right? X will become the next state, right? So this is a very simple circuit implementation of the input repeat detector, right? So now these two FSMs that we discussed in this lecture, these are just an example of a very simple FSM, just to illustrate what an FSM is, right? And we also saw the circuit implementation, and we saw that how we can derive the circuit, right? So typically in complicated circuit in VLSI design, when we make circuits in which say there will be lots of states, maybe 10 20 50 100 and so on, right? If the states are large, then of course we cannot do these things manually. We cannot manually design the next state function and the output function, which is basically the most important task in an designing an FSM, or designing an FSM, or designing a sequential circuit for a given FSM, this is the most important task. And typically for practical applications, for industrial applications, we do not do manually, right? So these things are done using EDA tools or electronic design automation tools, right? So these things are typically discussed in or how to model these FSMs mathematically. These things are typically discussed in the courses on Harvard description languages such as Verilog, right? So given a Verilog description of an FSM, there are tools or efficient tools which can generate this sequential circuit on its own. But the most important thing is that we should understand that given a scenario or given a description in, say, in English or in natural language, how can we convert that description to a mathematical model in using Verilog or other ways? That understanding you need to develop. So if you want to go deeper into these topics, you can look into these references. So just to summarize, what we have done in this lecture is that we have looked into an FSM, its the definition of FSM, its representation, and a few examples, right? So in the next lecture, we'll be starting with some different topic. We'll be first looking into semiconductors, and then we'll be looking into MOSFETs and so on. Thank you very much.